could be anything. Only we satisfy to call something a simply supported beam is that there is no restraint here. When there is no restraint here, the bending moment like this. So it's like this. It is free to move. For example, any node in a structure has 6 degrees of freedom. It can move in 6 different ways. 3 linear movement and 3 rotations. So it can move in this direction, in this direction, and in a direction perpendicular to the plane of this paper, and it can rotate in 3 different axes. So every node has 6 degrees of freedom. In this particular case, when you call it as simply supported, it is only restrained from coming down. It is restrained against gravity. It can move in all the other directions. So such a beam is called simply supported. So it cannot develop a momentum because it's not restrained. To understand this, if you are confused or if you are not able to understand, you think of a situation where someone is holding your palm tightly, and then when you try to move your joint, you will experience a force there, you will experience a pain there. So that is because you are being restrained. You are being restrained at the end. Your hand is held by somebody there tightly. So when you move your joint, you will experience a pain or restraint. So that is not pinned. When you are left alone, when no one is holding, and when you are moving your palm joint, then you won't feel any force, no pain. So that is a pin condition. So you are simply supported. So here, that is the condition. Your slab cannot come down, but it can move in all other directions. So that is simply supported, and it will bend in this manner. And I have derived the bending moment here from first principles. WL square by 8, this will be the moment at the center of the beam, and this is the maximum moment possible in the span. It cannot be more than WL square by 8. From first principles you can derive it. If W is the load on the beam and if L is the center to center span, the reactions would be WL by 2, and the moment will be WL by 2 into L by 2 minus WL by 2 into L by 4, that is react. So that is W into L multiplied by L by 2 by 2, so that is L by 4. So you get ultimately WL square by 8. Now this is simply supported continuous beam. All I can tell you is that since this is continuous, it will develop a moment at the joint, and once you have a moment here, you can logically conclude that the moment here would be less than WL square by 8, because for simply supported condition we have WL square by 8. Now when you have a continuity here, there is a moment developed here due to the continuity, and when there's a moment developed here, see someone is pulling you up, that means your span moment will come down from WL square by 8. So it is reducing, so WL square by 12. So those 22.5 in IS 456 gives you a thumb rule wherein you can find these values. So you can go to this close, you will get a table there in that close, and that table tells you that your moment at the first span will be WL square by 12, and in your second span would be WL square by 16. It is further less. This itself is less than WL square by 8, and the second span or the intermediate span will be lesser than WL square by 12 as well, because it's being continuous at both ends. Here it's continuous at one end, so it's getting reduced from WL square by 8. Now here it is continuous at both ends, so it is further reducing to WL square by 16. So this is how the thumb rule logically tells. Here WL square by 10, here WL square by 12, here WL square by 10. Again it's the first support, and at the end support it is generally assumed to be simply supported, and it is 0. It is not assumed, it is actually simply supported, and you have 0 here. For a cantilever beam, you have WL square by 2 as the moment, and WL as the shear force. You can again calculate this from first principles. When you have W as the UL, W multiplied by L is the total weight, and that will be acting center. So W into L is the weight, and that multiplied by L by 2 will be the moment, so WL square by 2. And the total load W into L will be acting at the single support, and that is the shear force. In theory, you generally call these frames as fixed. Now let us see how it behaves. See, in the first case, you have a frame and the columns are oriented in plan like this. So you have the width, say 230 or 200, whatever it is. Now see, this is the bending moment diagram. What you have 40 here, 40 here, and 60 at the span. All I can say is that this moment will be less than WL square by 8, because here you are developing a moment. You will have to do a frame analysis to establish this moment, either by Canny's method or moment distribution method, or by doing this analysis in ETABS you can arrive at these moments. Now let us rotate the column by 90 degree and at the same time maintaining a same center to center distance. Say the center to center distance remains same, and we have rotated the column. This time the depth or the larger dimension orienting in the direction. So there will be a change in moment. The moment at the support increases and the moment at the span reduces. Now why is this? This is because the stiffness of the column in this direction increases, or the fixity of the column increases, or the inertia of the column increases. So when the stiffness increases, when the fixity increases, your moment will develop more, and when the end moments are more, the span moments will reduce. So we can conclude that the stiffness of the member or the joint is going to decide the moment distribution. So it's no more a fixed beam, it's a partially fixed beam, because when you change the rotation or when you change the size of the column, there is a difference in the moment distribution. So this is a very important aspect that needs to be understood to do frame analysis. So this is the reason, one of the reason that we are going to use ETABS for the analysis, because you need to calculate the stiffness of joints. Now with this understanding, let us also look at orienting column for gravity load. So please note, this rule works for gravity load orientation columns. For lateral loads we may have to do a second check. So here you have a building, say this is the framing plan, and you have 4 meters, 6 meters, 3 meters and 3 meters. Now this first column I'm orienting it in this way because 4 meter is more than 3 meter. So the column needs more stiffness in this direction, or this beam will be having more moment at the end, and hence the column has to be oriented in this direction. Now when you come here 4 and 6, the final moment on this column is in this direction, because 6 minus 4 2, 6 is larger span and 4 is lesser span. So if you draw the elevation of that frame, you have a moment from 6 meter direction and you have a moment from 4 meter direction, and the net effect is 2 meter in this direction. So 3 meter is more than 2 meters, so I would prefer to orient it in this direction. The same way, when you come to this column, 6 meter is more than 3 meters, so I'm orienting it in this 6 meter. So 3 minus 3 is 0, so I'm orienting it in the 4 meter direction. Again 3 minus 3 is 0, 6 minus 4 is 2, I'm orienting it in this direction. This is again 6 versus 0, so I'm orienting it in this direction. Now this frame is similar to the above frame. Please note, based on gravity loads. This is the thumb rule. So as a beginner, you can start scheming in this manner. When there are lateral loads, there will be difference in orientation sometimes, because lateral deflection is going to be different. So what we can do is, as a thumb rule, start your analysis by orienting the columns in this manner. After that, you input your lateral loads, everything, and then check for the minor axis and major axis moment, and also the deflection for the lateral load in both direction, and then we can decide if we need to change the orientation. So as a start rule, as a beginner, go with a gravity load orientation. Next, let us get into what a simple